Lusztig tensor categories for affine sl2 at admissible levels and quantum groups. Yeah, please go ahead.
Okay, yeah, thank you, Sven, for the introduction. And I'm sorry that I can't be here in Montreal in person, but I thank the organizers for inviting me to give a talk anyway. So I thought I would talk about something, some work in progress with Jinwei Yang, which I hope will connect with a lot of the different topics that are being covered at this conference. So tensor categories, VOAs, and maybe a little bit of quantum groups as well. And yeah, I wanted to highlight some of these results because they have some interesting features that at least I'm not so familiar with, like the non-rigidity especially is something that's kind of new for me. So I think it leads to some interesting things. So let's start with a finite dimensional simple Lie algebra, G, and then a non-degenerate invariant bilinear form on G, which we always want to scale so that long roots have square length 2. Then we can form the affine Lie algebra. So loop algebra with a central extension of loop algebra with these brackets. And then there's this triangular decomposition. So we have a positive and negative parts of the loop algebra, and then the 0 degree part, which is just a copy of G itself together with this central element K. And we want to consider modules for affine Lie algebras. So we say that a module has level K if this central element acts by a scalar. And especially important, level K modules that we want to consider are these Weil modules or generalized Verma modules. Maybe for this talk, I'll call them Weil modules because that's shorter. So to create such a thing, we can start with a G module M. Doesn't necessarily have to be finite dimensional, but for our purposes, it will always be finite dimensional. We can make the positive part of G hat act trivially. We can have the central element act by this level K. And then you can form the Weil module as this induced module, induced from this module for the non-negative part of the affine Lie algebra. Almost always, we will be considering the case where M is a finite dimensional simple module for G, in which case we can label this simple module by a dominant integral weight lambda. So when we induce a G hat module from a simple G module, we don't necessarily get a simple Weil module, but that Weil module will always, for us, it will always have a unique simple quotient, which I will denote LK lambda. So K and lambda together basically are giving you the affine highest weight of this module. So with these Weil modules and these simple modules, we can define the Kazhdan Lusztig category as Kazhdan Lusztig originally defined it. There are different definitions of categories that people call KLKG, but this is the category that Kazhdan Lusztig defined. So that's what I will call that KLKG. It's the category of finite length G hat modules, it's level K, and the composition factors of these finite length modules are these coming from these LK lambdas. So yeah, sometimes it's convenient to introduce this shifted level kappa, which is K plus H check. H check is a dual Coxeter number, whatever that is. And so Kazhdan Lusztig, of course, they famously proved that if kappa is an irrational number or a negative rational number, then this category is a braided tensor category, and moreover, it's equivalent to quantum group category at some value of Q, which corresponds to kappa in this way. They explicitly did not consider positive rational values of kappa. So what about positive rational values? In this case, there are also some tensor category results, but usually it's for this actually very small subcategory, well, sometimes a small subcategory of KL upper K, which I would call KL lower K. Its objects are modules for what turns out to be some simple affine vertex operator algebra at level K. So a theorem so a theorem about this KL lower k category in the case that k is an admissible level in the sense of Katz and Wakimoto. So Arakawa proved that this KL lower k at an admissible level is finite and semi-simple. And let's see, it looks like there's a question. Does KL allow for Cartan subalgebra to act non-semisimply? So let's see, so in the Kazhdan Lusztig category, the Cartan subalgebra of G will act semi-simply because it acts because it turns out that all of the objects of KLK will have finite dimensional conformal weight spaces, which are finite dimensional G modules. Of course, K also acts semi-simply, but the other part of the Cartan subalgebra of the affine Kac-Moody algebra, which is corresponding to the Virasoro L0, does not need to act semi-simply. So there's no assumption about L0 semi-simplicity in this definition of KL. So let's see. Yeah, so that was about KL upper K. About this KL lower K is a subcategory which is finite and semi-simple at admissible levels. And then Thomas and Huang and Jinwei proved that it's also a braided tensor category at admissible levels. It's also known to be rigid in many cases. We certainly expect that this KL lower k is always rigid at admissible levels, in which case it would be a braided fusion category. So Thomas proved rigidity for simply laced G, and there's some other rigidity results for other cases. And conjecturally, this KL lower k would be equivalent to the semi-simplification of the quantum group category at this root of unity. And this conjecture is probably an easy exercise in some cases, like for type A, there's a classification of type A categories with type A fusion rules by Kazhdan and Wenzel. So you can probably just check that these are the same in that case. But sometimes this quantum group category is a modular tensor category, and sometimes it's not. So we would expect similarly this KL lower k is sometimes modular, but it's not always modular. Anyway, so that's kind of some of the highlights of what's known at positive rational shifted levels. But what I want to focus on is that the original category, the KL upper k category, just for G equals SL2 and for admissible levels. So for SL2, admissible levels look like -2, that's the negative dual Coxer number, plus P over Q. P has to be at least 2, Q can be anything if P and Q are relatively prime. Maybe I should briefly mention the P equals 1 case, that's not an admissible level, but we do also get a tensor category when P equals 1 and Q is a positive integer. But in that case, the category is just a co-cycle twist of the classical SL2 category. So it's not as interesting for the purposes of this talk. So right now I will summarize what are the results that Jinwei and I are obtaining about this category for SL2, and then I will get into a little more of the details of the detailed structure of this category and how we prove these results. So first of all, we prove that KL upper K for SL2 is indeed a braided tensor category, and the tensor category structure is the one for vertex algebras due to Huang, Lepowsky, and Zhang. Second of all, we show that every simple object of this category has a projective cover. So in other words, this category has enough projective objects. Simple objects are indexed by non-negative integers because those index the dominant weights of SL2. And so if we have an LKN simple module, we will call its projective cover PKN here. So that's the second result. Third, as indicated in the title, this category is not a rigid tensor category. But we do prove that it has an interesting category of rigid objects. In fact, an object is rigid if and only if it is projective. And as I said before, we have enough projective objects. So that means we do have quite a few rigid objects. Let me also mention that Allen, Lentner, Schweigert, and Wood have this interesting observation that when you have a tensor category that comes from a vertex operator algebra, which this KL upper K does, turns out, then you do get this weaker duality structure coming from what are called contragradient modules for the vertex operator algebra. And this weaker duality structure is called Grothendieck-Verdier category by Boyarchenko and Drinfeld. I think it's gone by other names in the past as well. But so we do have this weaker duality structure on the full category, and then we have this kind of small but very much non-trivial category of actually rigid objects. And finally, we can actually say something more about this category of rigid and projective objects. It's going to be tensor equivalent to the category of tilting modules for quantum SL2 at this root of unity that corresponds to the level. So in this case, it's e to the pi I q over p. So this last result that the category of tilting modules embeds into KLK actually gives us a nice universal property, because tilting modules have a nice universal property, and this category is embedded into KLK as a very nice subcategory. So so I guess to describe what this universal property is, first, so I guess the most basic tilting module is this two-dimensional simple module for the quantum SL2. And under this embedding, that gets sent to the Weil module, which is induced from the two-dimensional simple SL2 module. So this particular Weil module plays a special role in the Kazhdan Lusztig category. And basically, the universal property is that whenever you have any tensor category that has an object, a tensor category which is not necessarily rigid, that contains an object that looks like this Weil module, or looks like this two-dimensional simple quantum SL2 module, then you get a tensor functor. So what it means for an object to look like this Weil module, or this two-dimensional tilting module, is it's rigid and self-dual. Which means it has an evaluation going into the unit object and a co-evaluation coming out of the unit object. Then you can compose the two because this is self-dual, and then you get some scalar multiple of the identity. And if it's this particular combination of the root of unity and its inverse, well, that's the property that's satisfied by the two-dimensional simple quantum SL2 module. So whenever you have an object like this in a tensor category, you get a unique functor from KL upper K going to this tensor category. And it sends this Weil module to the object, the special object X. And this functor is a monoidal functor. It's also right exact, but it doesn't necessarily have to be exact. So maybe I should mention that quite a while ago, Ostrich observed that the quantum group category at this root of unity has a similar universal property with respect to rigid tensor categories. And then in that case, you get an exact tensor functor. And so Thierry Gann and Chris Negron used this result very nicely recently to get some tensor equivalences between quantum group categories and non-semisimple VOA categories. But in that case, that universal property is for rigid tensor categories, in which case you get an exact tensor functor. In this case, we don't require rigidity for the category C, but we do get, but I guess the cost is that the functor might not be exact. It might just be right exact. So some applications of this universal property, well, you can construct a lot of functors because it's easy to find categories that have objects that look like a two-dimensional tilting module. So for example, we can classify these Kazhdan Lusztig categories up to tensor equivalents or up to braided tensor equivalents. Just for example, if the k's, k and k prime, correspond to the same root of unity up to inversion, then basically the universal property says you get functors going both ways, and so they're equivalent as tensor categories. Their braidings might be different, but these categories don't have very many braidings, so you can easily determine, whether the braidings correspond also.
I had a question. Why do I get a tensor functor out of KLK and not just the tiltings? I mean, how do I extend from the projectives to the whole thing?
Yeah, you use the properties of projective objects. I mean, so the fact that you have enough projectives means that any object in KLK is a co-kernel of some morphism between projective objects.
Yeah.
So then you can send that object to the corresponding co-kernel in C. So, I mean, if you have a functor defined on projectives, you can always do this, and what you get is sort of right exact by construction. I mean, you're defining it in the unique way to make it right exact. Whether it's a monoidal functor is another question, and that has to, in that case, that has to do with the fact that tilting modules in KLK are actually a monoidal subcategory. So in particular, it includes the unit object. Well, I should say projective objects in KLK are a monoidal category that includes the unit object. That's something you don't get in the quantum group category, for example. I'll get back to that towards the end of the talk. So yeah, so you can get a bunch of functors. You can classify the categories KLK up to equivalence. You can get what seems to be a tensor categorical version of quantum Hamiltonian reduction, because this Hamiltonian reduction is something that would send affine sl2 modules, reduce them to Virasoro modules. And the Virasoro central charge corresponding to the level K is a CPQ central charge. Of course, I guess it's well known that at these central charges, you get a modular tensor category for the Virasoro algebra, but it turns out you also get a non-semisimple category of modules at this central charge, this non-semisimple category is also not going to be rigid, just like the Kazhdan Lusztig category. But in some upcoming work that I'm doing with my student here at Tsinghua, we are finding that this non-semisimple Virasoro category does contain some object X that satisfies this kind of property. So this is a functor. So we get a functor which looks like quantum Hamiltonian reduction. It probably is, but naturally isomorphic to it, but I'm not sure how to prove that. And then finally, the other thing we get is, I guess, what you could call a non-semisimple, I guess maybe you should call it a weak Kazhdan Lusztig correspondence. It's a tensor functor from KLK to the quantum group category at the root of unity. It's certainly not an equivalence in this case, because the Kazhdan Lusztig category is not rigid and the quantum group category is. But at least it is essentially surjective. And it's not just right exact, but it will actually be exact. So certainly it's not an equivalence, but we can kind of characterize its failure to be faithful. Basically, the morphisms that this functor sends to 0 are going to be the ones that factor through this KL lower k subcategory that I was talking about earlier. So you have something that's sort of close to an exact sequence of tensor categories, where you have the sort of like the KL upper k is almost like an extension of the quantum group category by this KL lower k category. And as I mentioned, this functor is actually exact, which comes from this weaker duality structure that I was mentioning earlier. We have these these things called contragradient modules, which turn right exact sequences into left exact sequences, this kind of duality. And that helps with showing this functor is actually exact. So these are the main results that we're getting. So now let me go into a little more detail about how we prove these things, and a little bit more about the detailed structure of this tensor category. So maybe temporarily, let's return to the case that G is any simple Lie algebra. It doesn't have to be SL2 at this point. If we want this category to be, this KLK to be a tensor category, first of all, the tensor product cannot be the usual vector space tensor product of G hat modules, because that doesn't preserve level. So instead, we use this sort of fusion tensor product, which comes from vertex algebras. So let me just briefly mention how this Kazhdan Lusztig category comes from vertex algebras. So first of all, there's this Weil module, which is induced from the trivial one-dimensional G module. And that has a structure of a vertex algebra. It's called the universal affine vertex algebra associated to G at level K. So this algebra, I think, has appeared in a number of the talks at this conference so far. And if the level is not critical, it's not the negative dual Coxeter number, then we have a conformal vector, which gives VKG structure of a module for the Virasoro algebra. And in that case, we say that VKG is a vertex operator algebra, or a conformal vertex algebra, if you prefer. So then it's not too hard to show that this Kazhdan Lusztig category has a nice vertex algebraic characterization. It's the category of finite length VKG modules, which are what we call grading restricted and generalized. The generalized means that these modules decompose into generalized eigenspaces for the Virasoro zero mode, L0. L0 does not need to act semi-simply as part of the definition of KLKG. So, but we do have a generalized eigenspace decomposition at least. And it's also grading restricted in the sense that these generalized eigenspaces are finite dimensional, and there's also a lower bound on the L0 eigenvalues. So that's the category of KLKG modules. Basically, you prove this by showing that the simple grading restricted generalized VKG modules are exactly the LK lambda, which are the ones that show up as the composition factors in KLKG. Okay, so if you have a category of modules for a vertex operator algebra, then the way you define this fusion tensor product is with intertwining operators. So an intertwining operator is some kind of map from the tensor product of two modules going into some sort of series, some sort of formal series whose coefficients come from a third module. And the series is allowed to have non-integer powers of x. It's also allowed to have finitely many positive integer powers of log x. I guess the most important axioms of an intertwining operator, well, there's this, in the affine Lie algebra case, you can actually express the axioms in terms of this commutator formula and this iterate formula, which tell you how the modes of the affine Lie algebra act or interact with the intertwining operator. So, this commutator formula tells you that if you have an affine mode acting on W3, you can write it as an affine mode acting on W2 plus some combination of modes acting on W1. Similarly, with this iterate formula, if you have a mode acting on W1, you can rewrite it in terms of modes acting on W3 and on W2. So you have these kinds of formulas. And then there's this L-1 derivative property, which is also quite important, which says that the formal derivative of this series is same thing as putting this L-1 from the Virasoro algebra inside the intertwining operator. So that's more or less what an intertwining operator is in the case of an affine Lie algebra. And so I guess to be a little bit more concrete about this, you might notice that if you take n equals 0 in the commutator formula, If you take n equals 0 in the commutator formula, what you get is this result that if you take some linear map that takes W1 tensor W2 and you map it to any coefficient of some power of x or log x in this intertwining operator, what you get is a G module homomorphism. So for example, you can consider these Weyl modules, which are induced from M1, M2, and M3. Mi is contained in the Weyl module as its lowest conformal weight space, the L0 eigenspace. And so you can get a G module homomorphism by taking some elements of these finite dimensional G modules, M1 and M2. You can embed them into the Weyl module and then apply the intertwining operator. You can set the variable equal to 1 to pick out the coefficients of powers of x, and then you can project that to this M3 subspace to get some map going into M3, and that's going to be a G module home. So the theorem that I proved a couple of years ago, which generalized some earlier results with Jinwei, and it's also a variant of some intertwining operator constructions of Franco Zhu and Haisheng Li, that under certain checkable conditions, which I won't get into, this map that sends an intertwining operator to this G module homomorphism is actually a linear isomorphism. So now we can define this fusion tensor product in terms of intertwining operators. It's defined as some module equipped with an intertwining operator that satisfies some universal property. Says that whenever you have an intertwining operator from W1, W2 going into a third module, W3, that corresponds uniquely to some G hat module homomorphism going from the tensor product module to W3. So this is similar to the universal property of tensor product vector spaces if you think of an intertwining operator as an analog of a bilinear map, and a G hat home as an analog of a linear map. So of course, the problem with defining a tensor product by universal property is that it doesn't show that this actually exists. But there is this nice theorem, a general VOA theorem by Miyamoto. And in the case of affine VOAs, what it says is that if you look at the category finitely generated modules for VKG, then this category is closed under the fusion tensor product. So it doesn't matter what G is, doesn't matter what non-critical level it is, you always get tensor product modules in the category of finitely generated modules. So remember remember though that the Kazhdan Lusztig category is finite length modules, which is not necessarily the same thing. So as an example, this result on intertwining operators I mentioned on this slide here would imply that under certain conditions anyway, the tensor product of two Weyl modules is just the Weyl module induced from the tensor product G module. So how do we get tensor category structure? So there's this theorem, which is mainly due to Huang and Miyamoto and then Thomas and Jinwei. So they basically, this is a specialization to the case of affine VOAs. What it says is that if this finite length category, which is KLK, if it's the same as a finitely generated category, which is the category which has tensor products, then indeed we do have a braided tensor category structure. So this kind of generalizes the Kazhdan Lusztig theorem, which applied to non-positive shifted levels and also irrational shifted levels. So let me say a little bit about this tensor category structure. The unit object is the VOA, which is also this Weyl module. The braiding is pretty easy to write down because you just need some way to turn an intertwining operator involving W1 and W2, one involving W2 and W1. That's fairly easy to do by this so-called skew symmetry operation, where you turn x into minus x using some choice of branch of -1, and then you have this exponential of L-1 factor involved. So this is pretty straightforward, but the associativity is much more subtle. Because if you want to think of some map that takes elements of this triple tensor product to this one, Well, to create elements of this triple tensor product, you have to compose intertwining operators in this sort of way. Then what you have to do is you have to interpret the variables in the intertwining operators complex numbers, and then pair with some kind of dual vector, and then you get some kind of series which you can show converges in certain regions. They converge because these series turn out to be solutions of some nice differential equations, such as KZ equations in the affine case. So then this associativity is really basically giving you this analytic continuation of this multi-valued analytic function on one region to a multi-valued analytic function on another region. So there's the definition of associativity requires these sort of subtle convergence issues, and it's much more difficult to prove that you have an associativity in this category. So that's why there are some conditions on this for this tensor category structure existence theorem. Okay, so to prove the theorem for KLK for SL2, we need to check this condition that every finitely generated module actually has finite length. And it's enough to show finite length for the vial modules because every finitely generated module has some finite filtration where the successive quotients are quotients of vial modules. So really it comes down to showing finite length for the vial modules. The vial modules in turn are quotients of Verma modules. So you have the Verma module induced from the some highest weight, which is highest weight n for SL2, and then level k. You have to quotient out some other Verma module to get the vial module to make sure you have this finite dimensional SL2 module in the lowest conformal weight space. So studying the vial modules amounts to understanding Verma modules, and in this admissible level case for affine SL2, the Verma modules are understood. I think in full generality, this is due to Malakoff. And the Verma modules have this kind of structure. These are the embedding diagrams for the Verma modules at the admissible level, -2 plus p over q. Most of them have this kind of braid type diagram structure because that's basically the structure of the affine vial group of SL2, which acts freely on the weight km when m is between 0 and p minus 2. These are the so-called admissible weights for SL2, which have shown up in other talks. And then when you look at these ones, these are kind of outside the admissible weight region. So the vial group doesn't act freely, and you get these simpler kinds of diagrams. But the main thing from the diagrams that you can see what happens when you want to get the vial module. If you want to get the vial module for this, you have to take this Verma module, and then you have to quotient out this Verma submodule here. And when you quotient out this Verma submodule, you get rid of almost all of this embedding chain, and all you're left with is 2 composition factors for the vial module. And similarly, for these chain types, if you quotient out the Verma module, you're left with an irreducible vial module. So the result on the vial modules, they are simple if P divides the dimension of the SL2 module that we are inducing from. And otherwise, we have some non-split sequence where the vial module is an extension of 2 simple modules. So in particular, all vial modules of finite length. That means finitely generated modules of finite length, and then that means KLK is a braided tensor category. So that's the way to prove that you have tensor category. Let me mention a few of the basic fusion products in this category. So just reminding you about the SL2 fusions, that if you fuse the 2-dimensional module with any finite dimensional module, you typically get a direct sum of 2 simple modules. And the same sort of thing is going to happen when we try to fuse 2 vial modules together, except it's a little bit more subtle. So usually, tensor product of WK1 with WKN is going to be a direct sum of the n-1 and the n+1 vial modules. Usually it's a direct sum, but sometimes the sequence is non-split, and it's non-split when P divides the dimension of the the sl2 module we're inducing from again. So it's the case where you tensor WK1 with a simple Weil module that you get a non-split exact sequence. So these are the simple ones here. So what happens when you do fuse WK1 with a simple Weil module, you get an indecomposable module. It will turn out to be a projective cover. So let's call this fusion product PKLP. And then we can fuse PKLP with WK1, and then a direct summand of that will be the next projective module. We can tensor PKLP plus 1 with WK1 again, and then we will get the next projective module as a direct summand. We can continue doing this. And in general, what we get is we construct all of these kinds of, all of these indecomposable modules, the form PKLP plus M. And they're non-split exact sequences. There's a Weil submodule and also a Weil quotient in these indecomposable modules. So in more detail, we can write down that this is kind of a staggered module diagram that David likes, where you write out all the composition factors, and they're arranged so that you can see which composition factors have higher conformal weight. So lower conformal weights are these two composition factors on the left, which correspond to the Weil submodule, and these upper two composition factors correspond to the Weil quotient. You can move between the composition factors using affine Lie algebra modes in this kind of way. And what's interesting is you can go directly between the irreducible quotient and the irreducible submodule. You can go directly between them using the nilpotent part of the L0 operator. So it turns out that L0 does not act semi-simply on these modules. So that means that they're called logarithmic modules in the sense of logarithmic conformal field theory. So we can summarize what are the indecomposable projective objects in this category. The first P minus one of them are going to be the non-simple Weil modules, WKM. And then every Pth Weil module is simple and also projective. And then we have these logarithmic modules, PKLP plus 1, which are the remaining projective covers. So most of the projective covers are going to be these logarithmic modules. Of course, I didn't really explain how to show that these are actually projective yet. So how to do that? Well, the first step is easy. You show that this initial Weil module, WK0, is projective. That's not difficult because it's a Weil module, which means it satisfies a universal property that's sort of similar to the property of projective modules. And not only that, it has the smallest conformal weights of any object in KLK. So combining those two facts is easy to prove that it's projective. The harder part of the proof, we show that this WK1 Weil module is rigid. That's not easy. I'll say a little bit more about that on the next couple slides. And then using fusion products, we have that PKN is a direct summand of taking, you get a PKN as a direct summand when you take n tensor products of WK1 with itself. So using the rigidity of WK1 and the fact that PKN is a direct summand, you get that PKN is rigid. So that's not too difficult. And then finally, there's this nice lemma that says that in any tensor category, it doesn't have to be rigid. If the unit object is projective, then all rigid objects are projective. So this is usually used in the context of rigid tensor categories, which implies that if you have a projective unit object, then the category is semi-simple. In this case, our category is definitely not semi-simple. So the only possibility is that this category is not actually rigid. But at least we do have these nice rigid and projective objects, PKN. So after completing this argument, we get that the PKNs are rigid and they are also projective covers. So all projective objects are direct sums of projective covers. So they are all rigid. So all projective objects are rigid and all rigid objects are projective. So let me explain a little bit how we prove WK1 is rigid. So to prove it's rigid, we need an evaluation going into the unit object and a co-evaluation coming out of the unit object. Co-evaluation is a little bit easier because we have this co-evaluation at the level of the finite-dimensional sl2 modules. And then M1 tensor M1, remember we have this kind of linear map. given WK1, we have this tensor product intertwining operator, which, and then we have this sort of projection to lowest conformal weight spaces. That gives us a way of mapping M1 tensor M1 into the fusion product of the Weil modules, and then we compose that with this sl2 co-evaluation, and then we induce this to a G-hat module homomorphism from the Weil module to get the co-evaluation. The evaluation is a little trickier because we have to divide it into two cases. In the first case, where P is greater than 2, then we can actually lift the evaluation for SL2 modules. We can lift the evaluation to a morphism between Weil modules. But in the case of P equals 2, we can't do this so easily because we actually don't get an intertwining operator such that pi of this intertwining operator is evaluation. So earlier I said there were certain conditions that have to be satisfied for this to work. And when P equals 2, these conditions are not satisfied. So we don't get such an intertwining operator, but we do get an intertwining operator going into the WK2 Weil module. And it turns out that LK2 is the irreducible submodule of WK0. So we actually can get an intertwining operator that factors through this irreducible module LK2. And then intertwining operators correspond to homomorphisms by universal property of fusion products. So we get an evaluation. But the evaluation in this case is not going to be a surjective map, interestingly, because the image is contained of the evaluation is contained in this irreducible submodule of the Weil module. So this is how we get an evaluation and a co-evaluation, but then we need to show that this rigidity composition is non-zero, and then we have to rescale it to get the identity, and then we'll get rigidity. I guess the important point to observe is that this rigidity composition does involve the associativity, and in this tensor category, associativity is very non-trivial. It comes from analytic continuation of these kinds of analytic functions. In this case, these analytic functions satisfy a KZ equation. So essentially what we need to do is we need to solve this KZ equation in some region and then expand it as a series in the overlapping region and kind of extract the rigidity from that calculation. This is a tractable problem because for WK1, the KZ equations are end up giving you second order differential equations. The regular singular points, which means you can solve them in terms of hypergeometric functions. And everything is known about hypergeometric functions, so you know how to expand them as series in different regions. In the case of P equals 2, let me mention these differential equations have solutions with logarithmic terms, which indicates that this intertwining operator in this case really is what we call a logarithmic intertwining operator. There really are logarithms appearing in the series. And in fact, in this case, this tensor product module is the logarithmic module PK2. Once you've explicitly calculated the rigidity, you can also calculate this so-called intrinsic dimensions, this composition of the evaluation co-evaluation. And what you get is this scalar multiple, which relates this root of unity and the inverse. So finally, let me return to that universal property I mentioned before.
Can I ask a question about so something in the middle of the proof? So the unit is non-simple in this category, is that right?
That's right. Yes, the unit is non-simple. Yes, that definitely makes, especially this rigidity, getting this evaluation map, it makes it much trickier than it is frequently when we prove rigidity for VOA tensor categories. Okay, so finally, let me return to this universal property. So this intrinsic dimension of the Weil module WK1 shows that this WK1 looks a lot like the two-dimensional simple module for quantum SL2, which is a tilting module. And this tilting module category has a universal property. So you get a functor, a monoidal functor from the tilting category to KLK, which sends this two-dimensional module to WK1. And So using the explicit structure of the tilting category in KLK, which is not too complicated in the SL2 case, we can show that this is actually a fully faithful monoidal functor. So it's an embedding, and the image of the embedding is a subcategory of rigid and projective objects. So then if C is any tensor category with an object that looks like the two-dimensional tilting module, we can get a tensor functor from the tilting subcategory to C, and this subcategory embeds into KLK. So then we can extend this functor to KLK, as I was mentioning before, because KLK has enough projectives. We can write any W as a co-kernel of a morphism between projective objects, some morphism F, and then we define FW to be the co-kernel of F of F. Similarly, we can define F on morphisms in KLK, and the result is a right exact functor. It's also a tensor functor because the projective objects form a monoidal subcategory in KLK. So in particular, if we take C to be the quantum group category, we get this functor from KLK to the quantum group category, as I mentioned before. Okay, so that's all I have. Thanks for listening, and I'd be happy to take any questions.
Thank you for your talk. Do we have any further questions?
I have first a remark. Your conjecture formulated on the first slides about this KL sub K and equivalence with the semi-simplified category. I thought it was proven by Finkelberg.
Yeah, so yes, I guess I should mention that, yes, of course, it was proven by Finkelberg in the case of integer levels. Yeah.
Okay, integer levels, right.
I should have mentioned. Yeah, I should have mentioned that. But yes,
all right, you formulated it for admissible. So okay, for admissible, it's more complicated to prove it, or it's just compared to integer level.
Yeah. So I don't really have a good sense of that, but I would say, yeah, in some cases it certainly has to be quite easy. For example, on type A, as I mentioned, we have this classification of rigid categories with type A fusion rules by Kazhdan and Wenzel. So you can probably just check that, these categories are going to be the same. Probably it's an exercise, and maybe there's some other cases like that as well. But in general, I'm not really clear on that, I would say.
Yeah. Okay. Thank you. I have another question.
Yeah. One of the issues is that we don't, in general, have rigidity for KL lower k. So that probably is an obstruction to proving the equivalence at the moment in the cases where we don't know rigidity.
I see. Okay. Do I understand correctly that your tensor unit in this KL upper K, it has a proper submodule, only one proper submodule, right? It has two subfactors, basically.
Yes, it has length 2, so it has a unique proper submodule.
Do you know fusion rules for these subfactors?
Yeah, I guess in principle the fusion rules should be determined by the fusion rules of the Weil modules and the right exactness of the tensor product. But we haven't really calculated them in general. One thing I will mention is that if you look at the simple modules, which are objects of the KL lower k category, then they will be the same as, I guess, what you expect, the same as for the KL lower k.
It will be quotient of your tensor unit, right? Tensor unit of KL sub k will be quotient of tensor unit of KL.
That's right, yes.
Right,
yeah,
but
so
the complicated fusion is for the submodule of your tensor unit. I'm asking what is tensor square of this.
Yeah, so we didn't compute that.
Okay.
In principle, maybe it should be computable, but we didn't try to do that.
Because under your functor, this guy goes to 0, right?
So under the functor, this submodule should go to the unit object, I think, of the quantum group category, I believe. Because the quotient goes to the LK0 goes to 0.
All right. Okay.
But I think that's right. But yeah, probably the submodule
right.
then go to the
Okay.
unit.
So David, you still had a question?
Hi, Robert. Thanks for the lovely talk. So you know, of course, that 15 years ago, there was a lot of work in the physics literature where they were exploring essentially the Virasoro analogues of what you've presented here. There's a little bit of literature on SL2, but very little. I guess my comment / question was, you mentioned at some point that you had a tensor quantum Hamiltonian reduction kind of equivalence thing happening. Is that an expectation or a theorem?
Yes. So this is, I guess you could say, it's a theorem in progress.
Okay.
So I guess I think I briefly mentioned this. So I have a student here who is working on these non-semisimple Virasoro categories from the VOA point of view, and we do get rigidity for certain objects. I believe in your papers from a number of years ago. Those are what you call the CATS modules.
Right.
Some of these CATS modules we can show, at least some of them we can show are rigid. In particular, the sort of the basic ones like the K21 and K12 CATS modules.
Yeah.
Those will be rigid basically by similar argument as this affine SL2 case.
That is wonderful. So if I can just follow up on that, sort of the image of the reduction functor here would be sort of like the first row or the first column of the extended CATS table for Virasoro. But of course, we'd be very interested in extending it to the full table, which is where you kind of see a lot more intricate structure. So do you think your techniques can be extended in that way?
Oh,
you can't do it upstairs because then you'd have to go to category O, which is not tensor, but downstairs you should be able to do it, right, for Virasoro. I'm hoping.
Yeah. I mean, right. So that's, so Virasoro is definitely more difficult than affine SL2 for these kinds of reasons. Yes, but anyway, certainly some partial results at least seem to.
Okay. Well, just one last comment. There was a conjecture that in this sort of downstairs Virasoro case, when you allow the whole extended CATS table, that the projectives would have Jordan rank 3. And I remember people saying that, but having no good reason as to why it couldn't be larger, except that in all the calculations it maxed out at 3. So it'd be nice if you could confirm that at some point, because it's 15 years and absolutely no progress.
Yeah, so definitely projectivity, proving, so in the Virasoro category, projectivity is very tricky because you have to choose the right subcategory where you will actually get projective modules. Yeah,
very true.
So that seems to be very tricky in these non-semisimple PQ categories. Yeah, but maybe some partial results. Yeah, we'll see what happens, I guess.
Anyway, thanks for a lovely talk.
Do we have any more questions?
Yeah. So does every object have a finite resolution by projectives? Or equivalently, every simple have a finite resolution by projectives?
Does every simple have a finite resolution? I guess.
Or by Weil modules?
Yeah. So I guess probably. I didn't really think about that. I wouldn't expect it necessarily. So definitely every simple has a resolution by Weil modules, which is not finite. I didn't think about projective resolutions particularly, but I wouldn't.
But the quantum group is not finite. But the quantum group is not finite, so we have quantum, right?
If you say something,
you have a functor to, you have essentially surjective functor to this Lusztig quantum group, right? And on that side, it's not finite. Projective resolution of simples is not finite.
No, you have a resolution by tiltings. You have finite resolution by tiltings. So projectives are like tiltings.
Yeah, for tilting modules, they are finite. They are finite lengths.
Okay. Well, I mean, the reason why I'm saying this is because if you have finite resolution by projectives, then you're proving that the derived category of modules for the Kazhdan Lusztig category is equivalent to the derived category of quantum group representations. And then you can just use, so you have some equivalence, and then this right exact stuff you get by like taking homology at degree 0. But I mean, we can talk about this later, but it's a point which probably is worth thinking about.
Yeah, I didn't think about that, but
Even if you don't have finite resolutions, you have some other equivalents. So.
Okay, so then let's thank the speaker again.